The last component of equilibria that we're going to talk about is KSP, the solubility product constant. Now, remember that equilibrium is basically, anytime we have an equilibrium, we have products and reactants both present in expression. The rate of change of reactants to products and the rate of change of products back to reactants produces the same amount, so there's no net change. And my equilibrium expression is written with products over reactants, which is what we see here. This is something we're used to seeing. Now, the second thing you should remember is that anytime we have solids and liquids, they never appear in an equilibrium expression because the volume, the molarity, the mass per volume is constant. It's a density. Density is used to identify substances. It doesn't change. So as I remove mass, my volume decreases accordingly. So that means when we talk about a solubility product constant, usually what we are looking at is we are looking at some kind of precipitate, some kind of solid that when left standing in solution will actually show a little bit of ionization, and that ionization is generally small. Solubility product constants do range, just like all equilibria, and the higher the KSP, the more ions we have in solution. Conversely, the lower the KSP, the more precipitate or the more likely it will precipitate in solution. And this is evidenced by the equilibrium expression for the solubility product. This means when we look at our rice table, the main thing I want to point out is if this is my solid, this never participates at all in our equilibrium because it's a solid. Remember, when we look at a rice table, we only look at what accompanies the equilibrium expression. So depending on what's going on here, you treat it just like any other equilibrium. You may have something initial, typically it may be 0. You're going to have a change, and then you would solve for your x just like you would in any other equilibria calculation. Now, since this is simply another equilibria expression, that means our Q is actually very important, because now our Q tells us whether a precipitate will form. So just like before when we compared Q to K, we know that it will determine the direction of our reaction, the direction the equilibrium may go, whether it is product favored or reactant favored. And again, the reason is because of our basic equation. It's just ions. So if my Q is equal to KSP, I'm at equilibrium, the solution is considered to be saturated. That means it's holding the maximum amount and equilibrium is established. And equilibrium is only established in a saturated solution. Now, if Q is less than KSP, that means I don't have enough ions in solution. So that means more of the ions will dissolve. If Q is greater than KSP, that means it's going to precipitate until it equals KSP. So what we're talking about is we're simply talking about that shift like we've talked about before. Here's my equilibrium where my forward rate and my reverse rate produce the same amount of product. I have no net change. And so when we talk about Q, it's where are we on this idea? If I'm way over here and I've got a lot of product, so my Q is greater than K, it's going to have to shift in that direction to attain equilibrium. If I'm way over here and my Q is way less than K, that means I've got to shift towards the products to achieve equilibrium. Now, as we talk about factors that affect solubility, the main thing to remember is that all of these factors have one idea in common. Each one basically has creates a shift in the equilibrium due to and a response that follows Le Chatelier's. So when we talk about the common ion effect, let's look back at our rice table. So remember that a common ion is simply, I'm going to put zeros here real quick, is simply another ion that's present from a different solution. So if I take my barium sulfate and I add a solution with more sulfate in it and I up this, let's say I have 0.1 to start with, well, I'm still going to have plus x, I'm still going to have plus x here, this is 0. And now I have x and I have 0.1 plus x. This creates, in essence, a mass quotient effect. In other words, we create something where we're going to have some kind of discrepancy Q and K, and we're going to see a subsequent shift. And if I add common ions to a KSP, to something that is already slightly soluble to fairly insoluble, by definition, this will always shift back towards the precipitate, and I will precipitate more of whatever the substance is. You can produce the same thing with pH. You can produce the same effect with pH. And this has to do with what's going on in terms of the, in some respects, some of the amphoteric properties, but in addition it goes back to that idea of conjugate acids and bases. So this goes back, let's deal with our basic anion here. So if I have something like silver hydroxide, which is allowed to stand at creates an equilibrium, if I add a strong acid to it, now remember a strong acid always deionizes, and so I end up with my ions. Well, chlorine, remember that chlorine is basically, it's such a weak base that it really has no effect. In fact, it's one of those weak bases that cannot change the pH of water, and this goes back to what we talked about in the previous section. So it's really irrelevant, but what does have significance now is the hydrogen right here. Oh, you cannot see yellow. Let's try green. Is the hydrogen ion, because that hydrogen ion will react with the hydroxide in my equilibrium expression. So now I have a new equilibrium being attained, OH reacting with the H negative, the hydroxide I mean. I'm going to produce water. Well, as this reaction proceeds, okay, as I take that hydroxide out, we have a Le Chatelier shift. We've changed the reaction, we've changed our Q, and so we see a shift in our equilibrium such that the solid here becomes more soluble because I shift the ions, because I'm literally stealing some of this hydroxide ion, so it has to account for that. And another thing that plays kind of a crucial role in terms of where we're going, because our first thought is, well, if I'm stealing hydroxide, I'm producing more silver ion, but remember about this chloride ion. We have tons of this chloride ion just kind of hanging out, so that helps to maintain the neutrality of the solution. So I'm eating up this hydroxide, but I'm creating a solution where the silver can just hang out in solution because of the presence of the chloride. We still maintain neutrality, but we still see a Le Chatelier's effect. In other words, we see a shift, as explained by Le Chatelier's principle, that as I remove this ion, I have to create more of it, and so that's where we get this shift forward. The point to notice here is that our basic anion is always increased. The basic anion solubility, back up, if our precipitate has a basic anion, its solubility is always increased by the presence of acid. Now, what's cool here is we know that pH will affect the basic anion and make it more soluble in an acidic solution. We also know that an acidic cation will be made more soluble in a basic solution. Well, typically speaking, when we think of an acidic cation, the first one that comes to mind is going to be ammonia. The second thing that better come to mind is that ammonia is always soluble, so you're never going to see a KSP involving ammonia. By definition, they're soluble. So what does that mean? When we talk about a substance with an acidic cation, what are we referring to? And this is where we actually have to expand our discussion to Lewis acids and bases. Now, and in fact, deal with complex ions. So now, when we talk about a Lewis acid and a Lewis base, what we're referring to is simply the abundance of electrons or the lack of electrons. In other words, we have extra electrons or we have electron deficiency. If I have a Lewis acid, it can accept an electron pair, and basically it has what we would refer to as empty orbitals. Now remember, empty valence orbitals, what that refers to is going back to that 4s, 4p, etc. So remember that iron, element 26, is normally a 4s2, 3d6, but if I have iron 3, I've actually lost one of my D's and everything's out of my 4s. So that means my 4s and technically my 4p are available to accept these electron pairs, and that's what we see when we talk about the formation of complex ions. And by the way, this is a very nice table. It's worth looking at. The other point I want to make before I continue with the Lewis acids is notice that we have formation constants, and these are known as whoops, try that one, Kf's. In other words, we have simply another equilibrium constant. That means, just like what we saw with KSP, just like we see with Ka and Kb and Keq, at some point there may be a Q involved here. So just keep in mind. Ultimately, the point in any case is that I have these empty valences that can accept pairs of electrons, and as long as I have something with extra electrons, like we see with ammonia, and I have something with the ability that's electron deficiency, like our boron trifluoride, or what we see with our, whoops, wrong thing, so like what we see with our cations, they can accept electrons. They act as a Lewis acid, and so that's what allows us to form this thing called a complex ion. Now, ultimately, the complex ion, what we call is we have an ion, metal ion, that is surrounded by some Lewis acid, Lewis base. Typically, the most common ones are ammonia. Hydroxide also acts as a Lewis base. Chloride can act as a Lewis base. Cyanide, anything that has these lone pairs of electrons that can fill orbitals. And what happens is we see very similar to what you saw with the removal of the hydroxide by the hydrogen when we added acid. Because we're removing the silver, we create another Le Chatelier's shift, and that's why it increases the solubility. So if I have something like silver hydroxide again, okay, and that's my solid, and I add ammonia, what I actually see is I actually see the ammonia, the NH3, reacting with the silver, and it pulls the silver out of solution, increasing, creating that Le Chatelier's effect where I ultimately increase the solubility because I shift it to the products, which are the ions, and I form a silver amide. I think that's how you say it. In any case, that's what's going on when we talk about Lewis acids and Lewis bases. And so this formation of these complex ions always results in an increase in the solubility because it's a Le Chatelier's influence. And lastly is the idea that these Lewis acids are metals here, these three specifically, at a certain point can be made more soluble through increasing hydroxides because aluminum hydroxide is actually insoluble. We know aluminum hydroxide is an insoluble precipitate, but if I keep adding hydroxide, I actually shift this such that I form a complex ion with aluminum and I get up to 6 hydroxides around it and it becomes soluble. If I add acid, I actually shift it the other way because the acid reacts with the hydroxide, pulls it from this compound, and I increase the solubility of aluminum. So that's all it means by amphoterism. So we see amphoterism both within acids when we look at something like our HCO3 negative, which has the ability to accept a hydrogen and form an acid, or lose a hydrogen and form a base. We see that same idea here in the formation of complex ions.